Welcome to our series on thermochemistry, and today we're going to look at heat, work, and energy. Let's take a quick recap on the definition of energy. Energy is often defined as the ability to do work. Work, being mechanical, is the application of force over distance. Mathematically, this is written as W, work, is equal to F, force, times S, the distance. Now remember, heat is also energy, and it is transferred by virtue of a temperature gradient. It's associated with kinetic energy due to molecular motion. What we're going to look at now is how Joules demonstrated experimentally that heat and work were connected. He demonstrated that they were interchangeable forms of energy. One of the great breakthroughs in the history of science was the recognition that heat was a form of energy. Since it was known that heat flowed from a hot body to a cold body, heat was often thought of as something fluid. It was Benjamin Thompson who discovered the true nature of heat as a form of energy while he was operating a factory for boring cannons. In the process of boring the hole in the barrel of a cannon, Thompson noticed the metal got hot. He was able to show that the only explanation for this phenomenon was that the work being put into turning the drill bit was actually being converted into heat. So the mechanical equivalent of heat, motion and heat are mutually interchangeable, and that in every case, a given amount of work would generate the same amount of heat, provided the work done is totally converted to heat energy. Joule later improved on Thompson's idea and attained a value for the mechanical equivalent of heat of 4.14 joules, which was very close to our modern one, which we know today as 4.184 joules, which is equal to 1 calorie. So here I have a schematic of Joule's apparatus for measuring the mechanical equivalent of heat. In the schematic you can see that a weight is attached to a piece of string which is attached to a paddle. So the work of the falling weight is transferred to the paddle, which causes the paddle to turn. The turning paddle or the work is then transferred into heat. That heat is absorbed by the water. By measuring the difference in the temperature of the water before and after the weight has fallen, allows us to put a mechanical value on the heat energy. SI units for energy is the joule, which is equal to 1 Newton meter. Another common unit is the calorie, the energy required to raise the temperature of 1 gram of water by 1 degree C. So 1 calorie is equal to 4.184 joules. Note or remember the food calorie, which is a capital C, is equal to 1,000 calories or 1 kilocal. So often when we're looking at energy in thermochemistry, it's not uncommon to divide a process into what's known as a system and surroundings. We define the system as the part of the universe being studied. The surroundings is the part of the universe that interacts with the system. The system is contained usually within the surroundings, and the universe is a combination of both your system and surroundings. So let me just give you an example. When energy changes are measured in a chemical reaction, the system is the reaction mixture, and the surroundings can be the flask or the room. Collectively, the two together then will make up the universe. To reinforce this idea, I have a diagram here which represents a system and a surrounding. So you can see I have a conical flask with a reaction mixture in it. That's my system. Then the conical flask and the container, the box that it's in, would be considered your surroundings. Both of those together then represent the universe. There are three main scenarios that we consider when contemplating a system and the surroundings. So these are an open system, where matter and energy can be transferred between the system and the surroundings. A closed system, where only energy can be transferred between the system and the surroundings. And finally, an isolated system, where nothing is transferred between the system and the surroundings. To help visualize these different scenarios, I have drawn 3 bottles, each containing water. The first bottle represents an open system. There is no cap on this bottle, therefore matter can be exchanged between the systems and the surroundings. The material that the bottle is made of allows heat to be exchanged between the systems and the surroundings, for example, a glass bottle. The second bottle represents a closed system. There is a cap on this bottle. Therefore, matter cannot be exchanged between the system and the surroundings. However, it's still a glass bottle, so therefore the material allows heat exchange between the system and the surroundings. The final bottle represents an isolated system. This bottle is closed, therefore matter cannot be exchanged between the system and the surroundings. The material surrounding this bottle prevents heat from being exchanged between the system and the surroundings. So an example of that might be a thermos flask. When we talk about energy, we often use the word internal energy. Internal energy is the sum of all types of energy, both kinetic and potential, of the system. Internal energy is usually given the symbol U. However, some other sources use the symbol E. So just to be aware, internal energy can be represented by the symbol U or E. Typically, we don't know the absolute value of the internal energy of a system. But that doesn't really matter, because all we're really interested in is looking at the change of the internal energy. And how do we find change? It's U final minus U initial. So delta U, which is the difference in energy or internal energy, is equal to U final minus U initial. Internal energy may be described as the capacity of a system to do work. The word energy is derived from the Greek word to work within. And remember, work is equal to force by distance. Work done on a system will increase its internal energy. Work done by a system decreases its internal energy. Mathematically, this is represented as delta U is equal to W. So the change in the internal energy is equal to work. In a chemical process, gas may be produced. As a result, the volume of the gas produced causes the system to expand. The mathematical expression for the change in the volume of a system at a constant pressure is P delta V. P for pressure, delta V for the change in volume. An increase in volume of a system indicates that work is done by the system. Let's have a look at an example where work is done by the system. An example of this would be the piston in a car engine. So there would be an initial volume and an initial pressure. When the fuel in the car undergoes combustion, the reaction generates a gas, and this gas pushes against the piston. So we have force by area. At a constant pressure, this causes the volume to increase, and it is represented by delta V. So the work done by the system is represented by W is equal to minus P delta V. W is work is equal to minus P, the pressure, times delta V, the change in volume. Work done by the system results in expansion. Delta V will be positive. However, because it's doing the work, our delta U will be negative because we're spending energy. So overall, minus P delta V will be negative. Work done on the system will result in contraction. Delta V will have a negative value. Delta U, our internal energy, will increase. It will have a positive value. Overall, minus P delta V will be positive. So the system is earning or it's gaining energy because the energy is being put into the system by the surroundings. We have just seen how internal energy is related to work. Now let's have a look and see how heat is related. Heat is the transfer of energy by virtue of a temperature gradient. Delta U, which is the change in internal energy, is equal to Q. Remember, Q represents heat. If a system is cooler than the surroundings is acting on the system. That means Q will be a positive value. Q will be greater than 0. If the system is hotter than the surroundings, the system is acting on the surroundings, Q will be negative or will be less than 0. So in our first situation, the system is cooler than the surroundings, it will absorb heat. Hence, heat will have a positive value. In the second situation, where the system is hotter than the surroundings, it will give off heat. It will lose some of its heat. So Q will have a negative value. You will notice from this presentation that a chemical process is always viewed from the perspective of the system. Energy leaving the system has a negative sign. There's a decrease in the internal energy. Energy entering the system has a positive sign because there's an increase in the internal energy. Energy, work, and heat are all related to one another, and they're related by the following equation. That delta U, the change in internal energy, is equal to Q plus W, which is heat plus work. So that brings us to the end of this presentation. In the next presentation, we're going to look at enthalpy. Thank you for joining me.